building powerful AI models. You know the trend, right? They just keep getting bigger.
Yeah, it's relentless.
And especially with multimodal large language models, MLLMs, which can understand and process images, audio, text, even video. Their versatility is incredible, but it comes at a massive scale.
Absolutely. These models are breaking down barriers between data types, leading to amazing capabilities. But, well, integrating and processing all those different modalities simultaneously requires a colossal number of parameters.
And that massive size creates a huge bottleneck deployment. Getting these giants to run efficiently outside of massive data centers, say on-edge devices or even just smaller servers, is a major challenge due to their memory and computational footprint.
Right. You can train them, but then what? You need a way to shrink them down significantly without sacrificing their unique multimodal skills. This is exactly where techniques like pruning come in, selectively removing weights from the trained model.
But standard pruning methods, designed for text-only LLMs, don't seem to cut it for MLLMs.
Not really, no.
And that brings us to the paper we're doing a deep dive into today. Tamp App, Token Adaptive Layerwise Pruning in Multimodal Large Language Models. It's a fascinating piece of research from a collaboration across universities, including UNC Chapel Hill, UIUC, MIT, UMass Amherst, and HCOEST.
Yeah, strong team. So for those looking for the quick summary, maybe we should unpack the core problem and their proposed solution in the first minute.
Good idea. Okay, the central issue this paper tackles is that state-of-the-art MLLMs are too big for practical deployment. And critically, they found that simply applying existing pruning methods designed for standard large language models doesn't work well for MLLMs.
The key insight from the authors is why that is. They discovered that MLLMs process different modalities, visual, audio, language, with distinct token behaviors that vary significantly from layer to layer. Standard pruning just ignores this nuanced dynamic behavior.
Right, so their solution is a new pruning framework built specifically for MLLMs, which they call Tamp, short for Token Adaptive Layerwise Pruning. It has two main clever ideas.
First, there's Diversity-Aware Sparsity. This component intelligently adjusts how much pruning happens in each layer. It's based on the diversity of the output tokens in that layer across different modalities. Layers showing higher multimodal diversity are deemed more critical and are pruned less aggressively.
And the second is Adaptive Multimodal Input Activation. This is about making the pruning decision within a layer smarter. Instead of just looking at all input tokens uniformly, it dynamically identifies and uses the most important input tokens from relevant modalities for that specific layer to guide which weights to remove.
And the punchline. Tamp significantly outperforms previous pruning methods on powerful MLLMs like LLaVA-NeXT and VideoLLaMA2. It's particularly effective when you need to prune heavily, allowing you to make the models much, much smaller while still preserving their complex multimodal capabilities.
Okay, that gives you the high-level view. Now let's really dig in and see the evidence they gathered showing why traditional pruning fails and explore the Tamp framework in more detail.
So as we said, the starting point is the observation that existing pruning techniques that work well for unimodal LLMs methods like Wanda or SparseGPT just aren't fully cutting it when you apply them to MLLMs.
They don't transfer well.
Right. The authors set out to understand exactly why this mismatch exists.
Their fundamental discovery is about the unique token attributes within MLLMs. It's not just a single stream of information. You have visual tokens, audio tokens, language tokens, and their internal representations interacting and changing throughout the network. It's complex.
They provide compelling visual evidence right away. If you look at Figure 1 in the paper, the top part is a TSNE visualization showing output tokens from audio, visual, and language modalities from a specific layer within an MLLM.
I see it. The red dots, audio, blue dots, visual, and green dots, language, aren't all mixed together randomly. They form these distinct clusters in the feature space.
Exactly. They're spatially separated. This visually demonstrates what the authors call the unique distributions of each modality within the model's internal representation space. A pruning method that treats all tokens or feature dimensions uniformly might miss this crucial separation, right?
Okay, so the internal representations for different modalities are fundamentally different. What else did they find?
Well, the bottom part of Figure 1 reveals another critical issue related to input activations, which are often used in pruning. It's a bar chart showing the cosine similarity of the L2 norm of tokens from each modality, visual, audio, language, against the total input activation vector for a layer.
And what does that tell us? It looks a bit complex.
It shows that when you have varying numbers of tokens from different modalities, which is common in MLLMs, like think of a video input with many visual frames and maybe fewer audio tokens combined with a short text query.
Right, the inputs aren't balanced.
Exactly. So standard input activation calculations, like just taking the L2 norm across all input tokens, can be heavily biased towards the modality with the largest token count.
So if your input has way more visual tokens than language tokens, the input activation calculation is dominated by the visual part. And that potentially gives you a skewed view of the importance of parameters that might be crucial for processing the language part.
Precisely. The authors show that in an example with many visual and audio tokens but few language tokens, NA and VNL, the visual and audio tokens have much higher cosine similarity to the total input activation than the language tokens. This bias, if you use that standard activation measure to decide which weights to prune, leads to suboptimal weight pruning.
Because you're not accurately assessing the importance of parameters relative to the relevant inputs they're processing across modalities in that specific layer. Got it.
Yeah. So the two big takeaways from their initial analysis are MLLM tokens have distinct representations based on modality and layer, and standard input activation calculations can be biased by token counts, leading to poor pruning decisions. Traditional methods ignore both of these.
And that logically leads them to Tamp. It's a framework explicitly designed to address these multimodal specific challenges by leveraging these unique token attributes. Figure 2 provides a nice overview of how the pieces fit together.
And as we highlighted in the summary, it has those two core components. Let's dive deeper into the first one. Diversity-Aware Sparsity, or DAS.
Okay, DAS.
Right. The goal of DAS is to move away from uniform pruning rates across layers. Instead, they want to prune layers differently based on how important they are for encoding rich, multimodal information. And they measure this importance using the diversity of the output tokens from that layer.
How do they define this diversity? Is it just like one number?
No, and this is where the multimodal awareness comes in. They define specific diversity metrics in equation 2. There's intramodality diversity.
Within a modality.
Yeah, measuring the average cosine distance within tokens of the same modality. How spread out are the visual tokens from each other, or the language tokens from each other, cell in the output feature space.
Okay, so how internally varied are the representations for visual stuff versus language stuff in that layer?
Exactly. And then there's intermodality diversity, SVL, which is the average cosine distance between tokens from different modalities, for example, visual tokens compared to language tokens. This captures how well the layer is integrating or perhaps separating information across modalities.
Got it. So they're looking at diversity within each stream and how the streams relate to each other. Smart.
And their empirical observations on this diversity, shown in Figure 3, are quite revealing. They plotted these metrics across different layer types within a transformer block, the projection layers in attention, the feed-forward network, and across the different blocks or layers of the MLLM.
What patterns did they find? Anything jump out?
Yeah, a few things. First, the diversity metrics, SVSA, SVL, are significantly different from each other, which kind of reinforces the need to consider them separately. Second, diversity varies considerably within a block depending on the specific layer type.
Oh, really? Like which ones?
This was particularly interesting in the multi-head attention MHA module. The value projection layer, vProj, consistently showed higher diversity than the query QProj or key KProj projection layers.
Okay, that's maybe counterintuitive. The vProj layer processes the same input as Q and K, but seems to be encoding richer, more diverse information for downstream use.
It does suggest the vProj layer is doing significant work in transforming the input representation into something rich and usable for the attention mechanism, potentially capturing more nuanced multimodal interactions.
Interesting. And the third point?
Third, diversity fluctuates across the different blocks, the layers, in the model, meaning some layers are just inherently more critical for encoding this complex multimodal information than others.
And the DAS strategy uses this insight.
Yes. Their DAS strategy quantifies a layer's overall importance as the average of these diversities, S equals SV plus SL plus SVL3. The amount of pruning, or sparsity level, for that layer is then set inversely proportional to this average diversity.
So layers that empirically show they're encoding more diverse multimodal representations, based on this metric, are pruned less aggressively, preserving more of their capacity.
Precisely. It's a straightforward but powerful idea. Let the data's behavior in the model guide how much you prune each part. And they do this efficiently using simple cosine distances, which avoids the computational cost of methods that rely on, say, gradient calculations.
Much more efficient. Okay, that explains how Tamp decides how much to prune in a layer. But how does it decide which specific weights to prune within that layer, addressing that input activation bias we discussed? That's the second component, Adaptive Multimodal Input Activation, AMIA.
Right. AMIA is designed to improve those per-weight pruning decisions by calculating input activations in a way that reflects each block's specific multimodal processing focus, not just the total input.
And they show this focus actually changes across layers.
Exactly. Figure 4 shows this clearly, plotting the average attention scores for visual versus language tokens across different blocks. Different blocks attend to visual and language inputs to varying degrees. Some heavily rely on visual input, others on language, and some seem to integrate both intensely.
So the relative importance of visual versus language signals isn't constant throughout the network. It depends on what that layer is actually doing.
Exactly. And Table 1 provides concrete evidence that this matters for pruning. They show that using different subsets of input tokens for activation calculations, like using only visual tokens, V, or only language tokens, L, for pruning decisions in specific blocks, compared to using both, V plus L, affects downstream performance differently depending on the task modality requirement.
Right, like a visual task versus a text task.
Yeah. This confirms that aligning the pruning activation calculation with the layer's modality focus is crucial.
Okay, so the standard approach of just using the norm of all input tokens is suboptimal because it ignores this layer-specific modality reliance. Makes sense.
Correct. The AMIA strategy is to dynamically select a small set of core multimodal input tokens that are most relevant for that particular block's function, and use those selected tokens to calculate the input activation XCC2 that guides pruning.
How do they pick these core tokens? It sounds like a non-trivial selection problem. Is it just random?
No, not random. They use attention scores as an indicator of importance. They start by taking the last row of the attention score matrix, A-neck of 1, which essentially reflects how much attention each input token received from the output side as an initial measure of a token's contribution.
So tokens that receive more attention are considered more important initially. Plausible?
Yes, but they refine this score, A, by incorporating contributions from neighboring tokens using equation 3. This helps capture local context and smooth the importance estimates a bit. Then, they use an iterative selection process.
Iterative. How does that work?
They repeatedly select the token with the highest current refined contribution score. After selecting a token, they apply a penalty to the contribution scores of its neighboring tokens. That's equation 4.
A penalty. Why?
It's a clever trick. It discourages selecting tokens that are highly similar or redundant with ones already picked. It encourages the selection process to find a diverse set of important tokens that cover the key aspects of the input distribution for that layer.
So you make sure the selected set captures the spread of important information, not just a few peak values concentrated in one area.
Exactly. They stop this iterative selection when the set of selected tokens C is judged to be a good representation of the overall distribution of original token contributions. They measure this using the maximum mean discrepancy, or MMD metric equation 5.
MMD, right.
Think of MMD here as a way to measure how different the distribution represented by your small selected set is from the distribution of the full set of tokens. They stop when the difference is below a threshold that accounts for the variation they observed in the output token space.
Wow, okay. That is a sophisticated way to adapt the pruning decision to the layer's specific multimodal input focus. It ensures that the importance calculation for pruning is guided by the most relevant inputs for what that layer is trying to do.
Yeah, and Figure 9 in the appendix even visualizes this, showing how the selected tokens vary across different layers and models. It really highlights how dynamic the process is compared to a static uniform approach.
Okay, they've identified the problem with standard methods, proposed Tamp with its two components leveraging multimodal token properties. But how well did it actually perform when they put it to the test? The proof is in the pudding, right?
Right. They ran experiments on state-of-the-art MLLMs, LLaVA-NeXT, an 8 billion parameter vision language model, and VideoLLaMA2, a 7 billion parameter model handling audio, visual, and language. Quite large models.
Yeah, decent size.
And they focused on pruning the large LLM backbone component, which is usually the biggest part. They also tested on LLaVA-Vision 7B params in the appendix, which handles interleaved images and video.
And they evaluated performance across a wide range of benchmarks to ensure they weren't just optimizing for one narrow skill.
Precisely. For LLaVA-NeXT, looking at tables 2 and 3, they use benchmarks covering tasks like visual question answering, chart reasoning with chart QA, and general multimodal understanding with MME. For VideoLLaMA2, tables 3 and 4 show they included audio QA, video QA, and audio-visual tasks. Really comprehensive.
And crucially, these were zero-shot evaluations. No retraining after pruning.
That's right, zero shot, which is tougher but more practical.
What baselines did they compare against? The usual suspects.
They used standard LLM pruning methods, Magnitude, SparseGPT, Wanda, and also recent MLLM-specific ones like EcoFlap and ALBOL. A good mix.
Okay, moment of truth.
Yeah.
And the results. Was Tampa consistently better?
Yes, the results were pretty strong. On LLaVA-NeXT, looking at Table 2 and Figure 5 at a significant 50% sparsity, meaning half the weights removed, Tamp was the best or second best across 6 out of 7 benchmarks. It showed an impressive 1.9 percentage points higher average relative performance compared to the strongest baseline at that 50% mark.
A nearly 2-point average gain while removing half the model. That's substantial, especially with no fine-tuning.
Absolutely. And Figure 5 really shows Tampa's robustness, particularly at higher sparsity levels. While other methods saw performance drop off sharply, Tampa maintained its capabilities much better at 60% and even 70% sparsity.
So it degrades more gracefully.
Exactly. At 70% sparsity, Tamp achieved 8.2% higher relative performance than the second best baseline. That's a big difference when you're pushing the compression hard.
So you can shrink the model even more aggressively with Tampa before you hit that performance cliff. Very useful.
Exactly. The findings were similar for VideoLLaMA2, the audiovisual one. Check Table 3 in Figure 6. At 60% sparsity, Tampa was top or second on almost all the audio, video, and audio-visual tasks, demonstrating 1.2 percentage points higher average relative performance. Again, Figure 6 shows its better robustness at higher sparsity.
Consistent results across different models and modalities then? They had an interesting hypothesis about why the OWL baseline struggled at high sparsity, didn't they? Because OWL is specifically designed for VLMs.
Yeah, that was interesting. OWL uses an outlier-based pruning strategy, which can be effective for some LLMs. But the authors hypothesized that because multimodal tokens in MLLMs have different distributions and potentially different outlier patterns compared to text-only tokens, OWL strategy just doesn't transfer well, especially at high sparsity.
Which really reinforces their main point, doesn't it? You need MLM-specific strategies.
Completely. And the approach generalized beyond just LLaVA-NeXT and VideoLLaMA2?
Yes, the results for LV1 Vision in Appendix B, that's Table 6, confirm this. Even with different modalities like interleaved images and video, Tampa outperformed baselines like Wanda and SparseGPT. It showed around a 0.3 percentage point lead in average relative performance over the strongest baseline there. So the core ideas seem applicable across the different MLLM architectures and modality mixes they tested.
Okay, impressive main results. Beyond the headline numbers, they conducted ablations to dissect Tamp and understand what each component contributes, right? Always important.
Absolutely. Table 4a clearly shows the contribution of both DAS and AMIA. Starting with the Wanda baseline, adding just Diversity-Aware Sparsity leads to a significant performance jump.
Okay, so DAS alone helps a lot.
Yeah. And adding just Adaptive Multimodal Input Activation also yields substantial improvements over the baseline.
Right.
And combining them gives you the full Tampa benefit, which really validates that both ideas are crucial and complementary.
What's also noteworthy there is that DASI's using relatively simple cosine distance calculations for diversity actually outperformed EcoFlap, which relies on more computationally expensive gradient calculations for estimating layer importance.
So DAS is not only effective, but also efficient.
Seems like it, yeah. Simpler can be better sometimes.
They also zoomed in on the Layerwise Sparsity aspect in Table 4b, didn't they? Yeah. Comparing different ways of setting sparsity.
Yes. They showed that their specific DAS strategy, the one considering intra and intermodality diversity, performs better than simpler layerwise strategies like just averaging diversity across all tokens or averaging importance within a block. This validates the granularity of their diversity measurement.
So the details matter.
They do. They also showed DAS could improve SparseGPT when integrated, suggesting the diversity concept is broadly useful.
And the analysis of where Tampa prunes, looking at sparsity ratios across layers that was in Appendix C, Figure 7 and 8 provided some cool insights into the model structure, didn't it?
Yeah, that was really interesting. Figure 7 shows the average sparsity for different layer types within a block, QKVO gate up-down projections. Consistently, the value projection layers, vproj, had the lowest sparsity.
Lowest sparsity meaning pruned less.
Exactly. Tamp identifies them as critically important across different blocks and models, preserving more parameters there. FFN layers the gate up-down projections generally had higher sparsity, which actually aligns with findings in LLM pruning, where FFNs often contain more redundancy.
So that earlier observation about vproj layers having higher diversity seems to correlate directly with Tamp deciding they're less prunable. It connects nicely.
Exactly. And Figure 8 shows the average sparsity trend across block indices, so depth in the network. Interestingly, Tamp's sparsity trend often differs from typical LLM pruning patterns.
How so?
Well, it seems to align with the attention distributions shown back in Figure 4 intermediate blocks, where both visual and language attention is high, tend to have lower sparsity, fewer parameters removed. This indicates their importance for integrating modalities. Later blocks might show different patterns as the model shifts processing focus, perhaps concentrating more on language generation, allowing for potentially higher sparsity in non-language parts.
That's a strong point. Supporting Tamp's adaptive nature, its pruning decisions aren't uniform but seem to reflect the changing multimodal processing demands as data flows through the network. Very cool.
And just quickly, Table 4C further validated the AMIA component, showing that using attention-based methods, both their attention variant and the full AMA, for selecting tokens to calculate input activations is significantly better than random selection. Picking important tokens based on their contribution really matters for guiding pruning.
Makes intuitive sense. They did touch briefly on structured pruning too, right? Removing entire blocks or heads. Was Tamp useful there?
Yes, Table 5 shows they explored applying their DAS component for estimating block importance in a structured block pruning setting, while their strongest results were definitely in unstructured pruning.
Where you remove individual weights.
Right. The DAS idea did achieve competitive performance in block pruning settings, suggesting the insights about token distributions might inform structured methods as well, even if it wasn't the main focus.
So it sounds like a really thorough investigation with compelling results, but they are upfront about the limitations, which is good science.
They are. Their primary focus was on unstructured pruning, where individual weights are removed. While effective for sparsity, as you said, this doesn't always translate directly to hardware speedups unless you have specialized hardware support.
Right. Sparsity doesn't always equal speed.
Exactly. Structured pruning, which removes entire groups of weights like neurons or heads, is often more directly tied to latency gains, and their structured pruning results weren't as strong yet.
Okay, so more work needed on the structured side for MLLMs, maybe using these ideas. Other limitations.
Also, their experiments covered vision, audio, and language, but MLLMs exist for other modalities like point clouds or molecules, and there are different architectural variants out there like Q-formers. They suggest evaluation on a broader range would help confirm the general applicability of Tamp.
Fair enough. Can't test everything.
Yeah.
And connecting back to practical deployment.
They note their analysis focused on the performance-sparsity trade-off, which is foundational, absolutely crucial. But they didn't directly measure hardware metrics like latency or throughput on specific devices. That's, the next critical step for actual deployment.
Okay, so summing it all up, what's the key takeaway from this paper for someone working with MLLMs? What should you remember?
The core message is clear. Effectively compressing MLLMs isn't a simple extension of LLM methods. It requires a deep understanding and explicit leveraging of their unique multimodal nature. Applying uniform pruning ignores critical differences in how different modalities are processed across different parts of the network. You just can't treat them the same.
And Tamp provides a solid framework for doing that through its Diversity-Aware Sparsity for layer-wise rates and Adaptive Multimodal Input Activation for selecting relevant inputs to guide pruning decisions within layers.
Exactly. The experimental results on state-of-the-art models strongly demonstrate its effectiveness and robustness, especially at aggressive sparsity levels, bringing these models closer to practical deployment.
Which is essential if we want these incredibly versatile models to move beyond research labs and into more real-world applications on constrained hardware.
Absolutely. It's a significant step in that direction. It makes these powerful tools potentially much more accessible.
Okay, so thinking about these findings on how different layers show varying degrees of reliance on specific modalities or different levels of diversity, like the consistent importance of vproj layers or the changing sparsity patterns across blocks, what could this research imply? Not just for pruning existing models, but maybe for designing new, potentially more efficient and specialized MLLM architectures from scratch.
Ooh, that's a really interesting path to explore, isn't it?
If we know certain parts of the network are consistently doing specific types of multimodal heavy lifting, could we build future models with this knowledge kind of baked in from the start?
That's a great question. These findings definitely suggest that not all parts of a monolithic transformer are equally critical for all modalities at all times. Understanding which architectural components or layers are essential for different aspects of multimodal integration or processing, well, it could inform the design of more specialized modules.
Or maybe architectures that are more asymmetric or tailored in their later layers based on the primary output modality.
Possibly. It raises questions about whether we always need uniform structures throughout, or if efficiency can be gained by specializing components based on their observed function, like identified through this kind of pruning analysis. It definitely gives us clues for future architectural research, moving beyond just scaling up standard blocks.
Fascinating. A lot to chew on there for model designers. Thanks for diving into Tamp with me today. That was really insightful.
My pleasure. It's important work in making these models more practical.